Hello everyone. Today we'll study about air refrigeration system. First of all, we'll talk about the benefits. It is light in weight compared to VR and VCR, and its application in very layman's is aircraft refrigeration, because the sole motivation for it is to have a lightweight refrigeration system in aircraft. There are various methods of air refrigeration systems. We'll start with simple air cooling system. This is the apparatus of a normal simple air cooling system. It has very minor appliances, such as every aircraft has conduit holes. There are small openings on the wings to let air in. An airplane approximately flying at some 35,000 feet of height, it will always have a very low pressured air. We need to first compress it to a high pressure. The thing is, to use an auxiliary compressor will increase the work done and will eventually decrease the COP. Hence, we will have small openings into the aircraft wings wherein the atmospheric air rushes into it. Aircraft on an average flying at a speed of some 800 kilometers per hour, the air moving opposite to it is also at the very same speed, so it will pass through it and it will undergo ramming effect. Ramming effect means the natural compression of air when it enters a system or a conduit at a very high velocity. So the air comes into the conduits, it undergoes ramming effect, it goes into the so after the ramming effect it compresses slightly. So here we can see 1 to 2 dash is the ramming effect. 1 to 2 is the ideal ramming effect, but due to irreversibilities and friction, the process undergoes from 1 to 2 dash. So here we can see that from point 1, P1 is the ambient air pressure, and it will go to P2 dash. P2 dash is the actual ramming pressure. So after the ramming effect takes place, the pressure of the air increases naturally without any work input. After that, it will be passed through the air main compressor. The main compressor is an auxiliary powered compressor wherein the shaft of the compressor is driven by the gas turbine. The gas turbine is driven by the flue gases coming out from this combustion chamber. The gases come into this, the shaft, the turbine blades rotate, it rotates this shaft, and the shaft eventually helps to work the main compressor. Now, as it passes to the compressor, it goes from 2 dash to 3 dash. Again, it was supposed to go 2 dash to 3, but due to irreversibilities in the system and unidealistic conditions, it will go from 2 dash to 3 dash. After going to 3 dash, it will go to the point 4. In point 4, there is a heat exchanger. The air coming out of the main compressor is inlated into a tube, which is a tube inside a heat exchanger. This obviously at a high pressure, the temperature of the air also increases. So to decrease the temperature of this air, it is passed through a heat exchanger, and inside the shell, this is typically a shell and tube heat exchanger. Inside the shell, the newly inputted air, the rammed air, which is very cool, it is just the atmospheric air. This air is inletted into the shell and hot air is into the tube. So this cool air takes energy out from this hot air and makes the air from the main compressor cool. So this air cools down, it passes to the cooling turbine, and after going into the cooling turbine, it is made to outlet into the aircraft cabin. So this is the whole nutshelled process of a simple air cooling system. Here we can move further. Here we can see ramming effect. As we told, it is the natural compression of air when it enters a system at a very high speed. Outcomes. What are the outcomes of a ramming effect? Compression of air naturally without any input work done. It helps increase the pressure and density of any fluid without any work input. So going with each process is one by one. 1 to 2, the isentropic process. As we see, it is a vertical line, and on x-axis we have entropy, so we call it an isentropic process, but it is an ideal ramming process. And considering the irreversibilities and friction into the system, the system definitely does not undergo 1 to 2. The system goes from 1 dash to 2 dash, which is an actual ramming process, which is not isentropic, but definitely it is adiabatic. So there is no loss of energy during this process. Now talking about the energy balance. So we know that as the system is adiabatic, there will be no losses into the system. So energy of the system is totally conserved and balanced. So talking about the kinetic energy, V square by 2000 for these units, as it is in meter per second, it was supposed to be joule per kilogram. So therefore we divided it by 1000 and multiplied it by 1000 to get it kilojoule per kg. We also know by the steady state energy equation that delta H equals the delta KE. So therefore H2 minus H1 equals V square by 2000. For H equals CPT, we put the values here, we rearrange the equation, we get this. We divide the whole equation by T1, so we get this equation. We also know that T2 equals T2 dash. Therefore, we replace T2 by T2 dash here. Then we get our first equation. Now we know that specific heat at constant pressure minus specific heat at constant volume gives us the gas constant. Therefore, using this equation, and we also know that the isentropic index, the isentropic constant, is equal to Cp by Cv. So we put Cp by Cv as gamma, and we know that we take Cp common. So when we take Cp common, this Cp goes into the denominator and this Cp comes out. This term is equal to 1 by gamma. Therefore Cp equals R into 1 minus 1 by gamma. This term equals to 1 by gamma. Therefore when we take the LCM, the gamma goes above and we have gamma R by gamma minus 1. We put this value of Cp into the equation number 1. Then we get this equation. In this equation we have T2 by T1 equals 1 plus V square into gamma minus 1 by 2 into 2000 into alpha R T1. But we know that A that is local sonic velocity equals under root alpha R T1. Therefore here being alpha R T1, here we have alpha R T1, we suppose it being A square because the value of A is under root of the product and we have just these terms. So we put A square here. We know Mach number is equal to flow velocity of any fluid divided by local speed of sound in the same medium. Therefore V by A equals Mach number. Therefore V square by A square equals M square. So we get a relation between T2 dash upon T1. T2 dash is the stagnation temperature, T1 is the static temperature. We get a relation between these two temperatures equal to 1 plus gamma minus 1 by 2 into Mach number square. Mach number is the speed at which the aircraft is traveling. Now we'll talk about now we'll go in detail about each and every process. We'll go 1 to 2. 1 to 2 is an isentropic process wherein we can use the following equation. Isentropic process means PV raised to gamma equals to a constant. We make V as a subject, we put it into this equation, we get this identity. Now due to the irreversibility in the system, as we discussed earlier, the system goes from 1 to 2 dash instead of 1 to 2 as we see here. It was supposed to go here, but due to irreversibilities it goes like this. Therefore P2 dash is less than P2. Earlier, if it would be an ideal ramming case and there would be no friction, then it would reach to a higher pressure, but due to the friction the system reaches a lower pressure. We can see here the ideal ramming pressure P2 is higher than the actual ramming pressure. So it shows that due to friction the system was not able to attain the ideal ramming pressure. So therefore P2 dash is less than P2, yet the temperature attained still remains same. T2 dash still is equal to T2. We can see here. the efficiency of ramming or the ability of the ramming to increase to give a rise to the temperature can be given by ramming efficiency, wherein the ratio gives actual ramming effect by ideal isentropic rise in pressure, that is P2 dash minus P1 divided by P2 minus P1. This is the ideal case, this is the actual case. Then going for the second process, that is 2 dash to 3 dash, which is the compression process, which takes place into the main compressor unit. It is equal to WC, that is the work done into the compressor, equals MA into CP of the air into T3 dash minus T2 dash. We can see here it goes from here to here, and both these temperatures are T3 dash and T2 dash. This is T3 dash and this is T2 dash, wherein MA is the air that flows through this main compressor. All the flow rate is just the flow rates used in all the equations is just the air, that the mass of the air or the flow rate of the air which flows through this compressor channel, main compressor channel. Now we'll go for the cooling process. Cooling process takes place at 3 dash to 4, from 3 dash to 4. Herein the cooling takes place, QR equals MACP into T3 dash minus T4. This cooling process is not the refrigeration effect. This cooling process is just the part of this heat exchanger. This is just the part of the heat exchanger. It is not yet the cooling process. It is not the it is not the QR. It is just a cooling process to cool down the air which is still into the system. Heat refrigeration effect only takes place when it gets out in the airplane cabin. Now we'll talk about the 4 to 5 dash process, which is the expansion process. 4 to 5 dash. Here it is an ideally it is isentropic, so it should be a straight line 4 to 5, but actually it is adiabatic due to the irreversibilities into the system, so it comes like this. It goes to 4 to 5 dash, wherein there is turbine work. Expansion is always done into in a turbine, so this turbine gives out some work, MACP into T4 minus T5 dash. This turbine helps us to rotate this fan. This turbine rotates, its shaft is connected to this fan, wherein the rammed air which is coming out from the shell is pushed back into the atmosphere, and after the turbine expands, this air is flown into the aircraft cabin. So here is where we will get from 5 dash to 6 dash. Here is where we will get our refrigeration effect. Here is where the cooling will take place. Refrigeration process, it will take place between 6 and 5, wherein RE equals MACP T6 minus T5 dash. As per the TS chart, we can see this is T6 and this is T5 dash. Here the QR, the refrigeration effect, will take place, and the COP, as we know, COP is QR by Win. Win is always into the compressor. We generally do not consider the turbine work because the turbine is not participating on upper hand into the process, or also the ramming effect. Ramming effect and the turbine work are not actively taking part in the compression, so we don't consider it. It is just a shadow part or one of the part of the refrigeration system, so it has to be there, but it is not to be considered on a first hand. So we will just consider the compression work here. Therefore it is QR by compression work, and hence we get it T6 when this gets cancelled out, and we get T6 minus T5 dash divided by T3 dash minus T2 dash. This was a simple air cooling system which is used for ground surface cooling or low speed flights. For higher tier cooling, we have some more complex systems which will be discussed in the next video. Thank you.